Hello and welcome. Today we're going to talk about something that's pretty much the bedrock of all the advanced tech we use, and that's trust. But I'm not talking about just a feeling. I'm talking about the actual, deliberate process of building it.
I mean, it's a huge question, right? Think about it. We've got microscopic robots that could one day be in our veins, and then there's the invisible cryptography that's protecting our data right this second. We are constantly relying on systems that are way beyond what we can see or touch. So, how do we actually get confident in them?
And that's really the core idea of this whole explainer. That feeling of trust, it's not some blind leap of faith. It's the end result of really rigorous, methodical, and honestly brilliant engineering. It's a system that's been deliberately built, not just hoped for.
Okay, so let's get into it. We're going to look at three very different case studies. I mean, they seem worlds apart, from the teeny tiny microscopic scale all the way up to the global. But what we're going to find are these common threads, these core principles, used to systematically engineer trust.
First up, we are going straight to the future. We're venturing deep inside the human body with nanomedicine. Yeah, we're talking about devices that are so small they can actually circulate in our bloodstream to find and treat diseases.
So the huge challenge here is something scientists call flow-guided localization. To put it simply, how in the world do you know where a nanobot is? If it finds a problem, you kind of need to know the location of that problem, right? It's like trying to get a GPS signal for a single grain of sand that's floating down a river.
Now, I know this diagram looks pretty complicated, but the solution here is just brilliant. You can't get a constant signal from something so small. So scientists took a totally different approach. They take the few little pings they can get and run them through two different processes. One compares the data to a huge training database, and the other uses pattern matching. Both of those feed into a model that reconstructs the nanobot's most likely location. It's all about turning a few faint signals into a data pattern you can actually trust.
This trust is built using a really clever two-step process. First, the researchers create what they call an analytical model. Think of it like a weather forecast that predicts the nanobot's path. Then, they test that forecast over and over and over again against a simulator, which is basically a super realistic digital twin of the human circulatory system. It's only when the model's predictions actually hold up in that chaotic, simulated reality that you can start to trust it.
And this right here, this perfectly illustrates our first principle. Trust is engineered by creating a predictive model and then smashing it against a simulated reality until you can prove it works. Okay, let's move on to our next case study and see how this pattern builds. We're zooming way out now, from the microscopic all the way to the global scale. We're talking about the data that runs our entire world, and the looming threat of quantum computers that could, theoretically, break all of our current encryption. The organization right in the middle of this whole challenge is NIST, the U.S. National Institute of Standards and Technology. Their job is to run this massive, worldwide competition to find and approve the next generation of cryptographic algorithms, the ones that can stand up to a quantum attack. So how do you get the entire planet to trust a brand new security standard?
Well, the answer is you do it slowly, you do it deliberately, and you do it completely out in the open. I mean, just look at this timeline. This thing kicked off way back in 2016, and it's basically a decade-long public battle royale. Cryptographers from all over the world submit their ideas, and then they spend years trying to break each other's work. It's this intense public gauntlet. Trust is literally forged in the fire of that global scrutiny.
And after all that time, you finally get to the final round. This table shows different kinds of algorithms, things like code-based or isogeny-based. Each one is a totally different mathematical approach to security. The one they picked, HQC, well, it didn't win just because it was a clever idea. It won because it survived this entire multi-year process of being attacked and analyzed by the best minds in the world, proving not just its security, but its performance too.
And this gets us to our second big principle. For these massive global systems that absolutely everyone has to rely on, trust is engineered through a slow, transparent, and even adversarial process of public standardization.
All right. For our last case study, let's bring this all the way down to a super practical, everyday example from the world of software development. How do we trust the automated processes that build, test, and deploy the software we're using every single day?
We trust them by having other tools that are constantly checking their work. This is a tool called ActionLint, and its job, just like the quote says, is to validate GitHub Actions workflow files. Those are the scripts that automate how software gets made. The best way to think about it is like a spell checker, but for automation code. Before a really complex automated process is even allowed to run, where it could potentially cause a huge problem, ActionLint scans it for all the common errors, typos, and logical mistakes. It's basically a safety net.
And the whole process is incredibly simple and automated itself. As you can see, a developer adds just one little line of code to their workflow file. And from that point on, every single change they make is automatically scanned for errors before it can ever be deployed. It's this one simple check that prevents tiny human errors from becoming massive system failures.
And this brings us to our third principle. We build trust in these complex, automated systems by layering more automation right on top of them. Specifically, automated tools that are constantly validating and checking for mistakes before they can do any harm.
Okay, so let's recap. We've looked at nanobots, quantum cryptography, and software code. 3 totally different fields, right? But as we're about to see, these aren't just 3 random examples. They're all part of the same toolkit for engineering trust.
And here they are, the 3 pillars that connect everything we've talked about. For the invisible world of nanobots, we used predictive modeling. For the global infrastructure of cryptography, we relied on public standardization. And for the automated software pipelines we use every day, we built confidence with automated validation.
And this is the really powerful takeaway here. It doesn't matter if you're talking about the veins inside our bodies or the data that lives in the cloud, the challenge of creating reliable, trustworthy tech isn't solved with some kind of magic wand. It's solved with a clear, repeatable engineering process.
Which, of course, leaves us with one last big thought. We've seen how these principles apply to the microscopic, the digital, and the automated. But as AI and other technologies get even more powerful and autonomous, what's the next great challenge? What is the next frontier where we're going to have to deliberately and very carefully engineer trust?